right, how's everybody doing this morning? Cool. Okay, so today we're going to start with a quick review of the Bobot navigation. So we'll talk about the course that the Bobots are supposed to go on and how they're supposed to park at the end. Some people were able to finish last time, that was awesome. A lot of people weren't able to finish, and that's totally fine. Like I said, last time we had 2 classes to work on it. So we had the class last time, and we'll have the class this time as well. So if you haven't finished yet, that's totally fine. You can work on the navigation this whole class and just try and finish it by the end of today. Okay? If you were able to finish last time, then there is an extra credit program that you can work on. And that has to do with the navigation with Whiskers. So remember at the beginning of the semester, I showed you this little robot, and I showed you that it could roam around and navigate. And when it bumped into something, it could back up, turn around, and go a different direction. So that is the extra credit. If you have some time today, if you finished last time, or if you finish early on today, you can work on this extra credit assignment, and you can put the Whiskers on your car and load the program on there, and then make the car drive around and get extra credit for that. So that's what I'm going to talk about in lecture today, the Whiskers. This is going to be a relatively brief lecture, like we had last time, because I want you to have as much time as possible to do the fun stuff, building the robot and playing with it. So, relatively brief lecture, but we're going to talk a little bit about how the Whiskers work and how you can build them onto your robot, and how you can have a program to actually read data from that and decide where to go. So that's going to be our main topic for today. And then for the lab preview, I'll show you where you can find the assembly instructions, where you can find a test program to make sure that your Whiskers are working properly, and then where you can get the main program to actually load onto the robot. Now in the past, we've kind of given you a basic starting program, and then you've had to modify it a little bit. With the Whiskers program, you actually don't really have to do any modification. The program is written for you. You just have to load it on, and then it should work if everything is assembled correctly. So that's what we will be doing today. Are there any questions before we get going? Okay. Yeah?
If we're not able to do the extra credit Whiskers today,
right,
will we be able to do it in the future in like the open lab sessions?
Possibly. Most things are totally fine for working on during the open lab sessions. This is the last day that we're going to be working with the Bobot kits. So at the end of today, you should take everything apart and put it into your kit. So I would just have to check with our lab technicians about whether we'd be able to get those kits out of storage.
Okay.
Yeah. Other questions? Okay. So then let's start with a quick review of the Bobot and navigation. So you remember from last time, what we did is we programmed these Bobots to follow a course. And the course looked like this. You had a starting line, and then a little line partway along, and then another leg here. So each section of this course was broken, or was called a leg. So this was leg 1, leg 2, 3, 4, 5, and then this is the parking spot at the end. So the goal for your robot was to start here at the starting line, drive forward for leg 1, reach the second line here, pause for 3 seconds, beep, drive forward for leg 2, turn, drive
drive this way, and then at the end, it was to turn left, and then back up, and end up in the parking spot.
So that's what you worked on last time.
Some people found that their robot didn't go perfectly straight ahead along these lines. Sometimes the robot had a tendency to curve a little bit to one side or the other. So if that happened, one thing that you could do was you could make one of the motors run a little bit more slowly, and that you can play around with the different speeds, and hopefully that can compensate and cause your robot to drive straight on the track. Now, that being said, the carpet is a little bit uneven, and that kind of throws a little bit of variation into these runs. So even if you have a perfect program, it might not run exactly the same way every time. So, so you just have to play around with it a little bit, and do expect a little bit of variation. So that was the main goal from last time. Were there any questions about that? Okay. All right, so that was our brief review of the robot navigation. As I said, you can work on that for the entire class period today, and that's totally fine. Just try and finish up by the end. If you finished that last time, or if you finished that early on, you will have time to work on this extra credit assignment, which is the Whiskers. So the basic idea for the Whiskers is that we want our robot to be able to drive around, and if it bumps into something, it should be able to kind of navigate away from it. So in particular, if it bumps into something on the right, we want it to be able to back up and turn to the left, go away from that. And vice versa, if it bumps into something on the left, it should back up and turn to the right, kind of go away that way. So that's what we want. We're going to use these Whiskers to achieve that. Now, at the programming level, what that means is we need a program that will kind of cruise along for a while until it detects something from the outside world. And so it should be able to have something that detects if you bump something on the left, or some other indication that you bump something on the right. So when we did our windshield wipers assignment, we used inputs to detect something from the outside world. And that's what we're going to do again. We're going to use an input to detect whether the left whisker or the right whisker has been bumped. So remember, an input was a little pin on the robot, and it could detect high or low voltage. So and then our program could read that voltage and make a decision based on what to do, or based on what it was sensing. So an input would be something like one of the pin numbers. So we could call that pin 5, say, and that would be an input to that could be an input pin. Okay? And this pin, it doesn't directly detect motion or force. What does this pin actually detect?
A difference in voltage?
That's right. Yeah, it detects different levels of voltage. So it can detect whether the voltage is high or low. So so the basic circuit is something that needs to create either a high voltage or a low voltage at this pin. Okay. So when when we built our windshield wiper circuit, we had kind of a very basic switch there. So what we did is we had ground down here, and then we had a switch like this, and when the switch is closed, it's essentially a direct connection between this pin and ground. Now ground is at 0 volts, and the voltage is constant along any wire. So when the switch is closed, it's making essentially a straight wire from ground to this pin. What voltage would we have at that pin? Well, not 5 volts. It's connected directly to ground.
Oh, yeah.
0 volts, exactly. So when the switch is closed, we get 0 volts there. So that sounds good. We're creating a low voltage. But there's a problem with this circuit. Yeah.
Is this an if-else situation?
Yeah, that's right. So in the program itself, it would read this pin and do one thing if it saw 0 volts, and do something else if it saw 5 volts. Yeah. Oh, okay, I see. Is that just for today?
No, it's for,
Okay.
because of earthquake structural analysis.
Okay.
And so I don't know if it's forever, if they're going to reinforce it, or forever, like, good term there.
Okay.
But it's for
Okay.
a while.
Okay.
So those classes are supposed to be online for 2 weeks,
Okay.
but that may affect the
Yeah. Gotcha. Thank you very much. Okay. Lynn just told me that there has apparently been an announcement that there will no longer be classes in Davies Hall because Davies Hall has been determined to be structurally unsound and prone to earthquake damage. So starting now for some period of time, there will no longer be classes held in Davies Hall. So he was saying that those classes will be now spread out throughout the remaining classrooms on campus. And so they may be coming into these buildings and other buildings. So that's all he was saying.
Does that increase the amount of hours that we're in here? That's it.
No, I mean it won't affect our class. We'll still be in this class at the same times and doing the same things, but we may have to, move our stuff out of the way so that other people can use the classroom when we're not here. Yeah. Okay, so going back to our circuit here, the program looks at this voltage. It would go straight if it saw a high voltage here, and then if there was a low voltage, that would tell it that it's bumped into something on the right, for instance. So let's look at this circuit. So far, when the switch is closed, we have 0 volts here, so that's good. But there's a problem. What voltage do we have at this pin when the switch is open? Is that pin connected to 0 volts? No. Is it connected to 5 volts? No, there's no connection to 5 volts there. So what voltage is that going to be? It's kind of a trick question.
Zero.
Huh?
0?
Well, it might be 0. It could be 0 for some of the time, but there's nothing holding it down to 0. So it could also kind of float up and be 5 volts for some of the time. If they're, depending on, if there's static electricity, nearby, or somebody walks by and brushes against it. So it could go up to 5 volts, it could go down to 0 volts, and it can float around and change those voltages, go to high voltage or low voltage at unexpected times without really any way of knowing when that's going to happen. So, and our program is making decisions based on this voltage, right? It's going to go straight if it sees a high voltage, and it's going to turn to the side if it sees a low voltage. So if this pin isn't tied to anything, those motions can happen kind of at random times. It might be going straight for a while and then suddenly turn right for no apparent reason and then start going straight again. So is this a good circuit to use for this?
No.
No, exactly. So this is bad because we have a floating voltage at that pin. When that pin is not tied to anything, that's what we call that floating, because it can kind of float up or float down at random, unexpected times. So that circuit isn't great. So that's a problem with that circuit. So we need to find a solution. So the basic problem was that when the switch is open, this pin is not tied to anything. So you might say, okay, my first thought would be, all right, well, let's tie that pin to something. So we could have another circuit like this. We could have pin 5 again is our input. Still have our switch here, and we could have our 5 volts, which is also known as VCC, and we could connect that to our pin. Now, when the switch is open, what is this pin connected to?
5 volts.
5 volts. So what is this voltage going to be when the switch is open? 5 volts. So that's looking good. Is that problem solved now? Or is there maybe another problem with this circuit? Yeah.
Do we need to add a resistor in there?
Ah, yeah. Right, because what happens now when this switch is closed? Is this pin connected to 5 volts? Yes. Is the pin, we've now closed the switch, so we've essentially created a wire from here to ground. So is this pin connected to ground?
Yeah.
Yeah. So when the switch is closed, essentially you've got a straight wire from 5 volts to ground. And does anybody know what we call that when you have a wire from power to ground? Yeah.
A short.
Short.
That's right, a short circuit. So this is, when you have a wire from power to ground, that's a short circuit. And what happens is that wire allows a ton of electricity to flow from 5 volts power to ground. There's essentially nothing slowing it down. So it just floods tons of electricity. And when a lot of electricity flows, things heat up. And that results usually in damage or destruction. So if you have a short circuit, that's going to probably destroy your power source. Okay? So this is bad. This circuit is bad because it creates a short circuit. Okay. So we need to think of something else. So so somebody already mentioned we could put a resistor in there. So we could have our input here. And our switch. And then we could have a resistor here. And this value of this resistor is usually about 10 kiloohms when resistors are used in this way. So getting closer here. So now, when this switch is closed, this pin, there's a wire directly from this pin to ground. So when the switch is closed, what voltage are we going to have at this pin? Well, this ground, is 0 volts, and the voltage is constant along any wire. So when we've got this 0 volts down there, and the switch is closed, it's acting like just a regular straight wire, and so we would have 0 volts at this pin as well. This resistor allows a little bit of current to flow through, but it limits that current, so it no longer is going to draw so much that it's going to damage anything. Okay, so when the switch is closed, we have 0 volts at this pin. When the switch is open, that's like no connection. That is no connection to 0 volts. We just have this resistor that is connected to 5 volts, and that now allows this pin, it pulls it up to 5 volts. Okay, so when we use a resistor like this, we call this a pull-up resistor. So that's looking pretty good. When the switch is open, we have 5 volts there. When the switch is closed, we have 0 volts. Okay, so that's looking pretty close. But there's still one minor little problem with this circuit. And that is that somebody might write a program and accidentally make this pin an output instead of an input. And if they accidentally made this, say they accidentally made this pin an output and made it put out 5 volts. Okay? So they've written this program, this pin puts out 5 volts, and now the switch gets closed. Now you've got 5 volts coming out here, connected directly to 0 volts. So what do we call that again? Short circuit. Short circuit. So now, again, you're creating damage, not to the power supply this time, because we've got this resistor between the power supply and ground, but now you would damage or destroy this pin, because too much power would be coming from this pin. You'd have a short circuit. So this one is also bad because you could have a pin short circuit. So we need to put in one more thing. So just like we use a resistor here to protect the power supply, we can use a resistor here next to the pin to protect the pin. So we still got pin 5. Now we put in a resistor here. And this one only has to be, well, it can be relatively small. So 220 ohms, I think, is what's used in this case. So we've got a resistor there. We got a 10 kilo ohm resistor there. We've got our switch. Now, when we use a resistor like this between a pin and 5 volts, we call that a pull-up resistor. Because it pulls the pin voltage up to 5 volts when the switch is open. Okay. So here we are. we've got our pull-up resistor that's pulling this voltage up when the switch is open. We've got this other resistor that's protecting the pin in case somebody accidentally made it an output instead of an input. Yeah.
Why you don't put the resistor near the switch? It will work for both of them. And we put two resistors.
Why don't we put this resistor close to the switch?
Yeah, just one resistor near to the switch.
So
I think he needs
At
to
the
grab.
bottom.
oh, right there.
And then we only need one resistor for both of them.
Yeah, that's a good point. We could have done it that way. I don't know why they didn't do that. So, well, that's an improvement. That would be better. So you could do it that way as well. So you have in 5, and then a resistor, and then switch. Oh, okay. Well, and then 5 volts. In this case, if you made this an output and you force this to be low, then you would still have a short circuit from 5 volts there, and that could still damage the pin. So you would still, so that wouldn't quite work, but you're thinking, I like the way you're thinking. Yeah, there's often many different ways to make circuits, and often many different ways will work. So it's always a great idea to think about different ways you can do it. And yeah, if you can save a resistor here or there, simplify your circuit, that's awesome. Yeah.
Is there a way to put a resistor at a meeting point?
Like at a junction?
Yeah.
Not really. A resistor has two ends usually.
There's no like there's no resistors. Not that we would ever use, but there's no resistors that can take in two areas.
I mean, I suppose you could have like a square of resistive material and solder onto different sides. I've never seen that used in practice though, but it's an interesting idea. Yeah. So this is the final circuit that is used for our whiskers. Okay. So the 10 kilo ohm resistor pulls up that pin voltage when the switch is open. This 220 ohm resistor protects the switch if it's used as an output, or protects the pin, and then the switch, when it's closed, pulls this pin voltage down to 0 volts. So when the switch is open, the voltage is at 5 volts. When the switch closes, the voltage goes to 0 volts. And the pin voltage is never floating. It's always predictable. And predictable is what you want, especially when you're controlling movement and things based on that. Okay? So this is the circuit. Now, the last question here is, we've been talking about this switch all along, but our robot doesn't really have any switches on it. It has these whiskers. So the question is, how do these whiskers relate to a switch? Or can they be used like a switch? And the answer is yes. The resistors act as switches. So, the whiskers act as switches. So let me show you how that works. So we've got our pin here and our little resistor, and what we have is we have the chassis of the robot, and the whiskers are attached to the chassis with these these poles. So they're bolted directly onto the chassis. So the Whisker goes something like that, and then it comes out like this, and then goes across, and has a little circle at the end. So the chassis, the Whisker is bolted to the chassis, and this chassis is grounded. So this end of the Whisker is grounded. And the Whisker is hovering right above the breadboard on the Bobot. And in the breadboard, we push these three little wires that are called a 3-pin header. So we take these little wires and we shove them into the breadboard in one of these rows. So if you're looking at it from the top, it looks like this. We've got these three little wires that are embedded in the breadboard, but which are sticking out. They're sticking straight out of the breadboard like this. So then, what happens is that, and this row of the breadboard is connected to this point on the circuit. So, when you're in the normal driving position and there's nothing touching the Whisker, it's kind of sticking out like this. And so you've got this pull-up resistor that's pulling your pin voltage up. So what is your pin voltage when you're in the normal driving position? 5 volts, exactly. So you're driving along, you should see 5 volts there, high voltage. But when you bump into something, it pushes this Whisker back a little bit, and now the Whisker bumps into this header that is sticking out of the board. So now you've created a connection between this header, this row, this point on the circuit, and ground. So now, that's like when we close this switch. So when you bump into something, this Whisker closes a switch from this point to ground. So what does this voltage now become at the pin? 0 volts, exactly. So that's how it works. So that's how the Whisker acts like a switch. When you're driving along, it's away from these pins, this header, and your pin voltage is high. When you bump into something, the Whisker gets pushed back, it closes the circuit, pulls that voltage down to ground, and you get a low voltage. Okay? So that's how the circuit works for the Whiskers. So, so any questions about that? Yeah.
So basically, we're going to be assembling 2 separate circuits, one for each sensor.
That's exactly right. That's exactly right. So I've shown you this circuit, and like you mentioned, that's kind of half of what you want. That would be the left Whisker. You'd have to replicate this and use a different pin for the right Whisker. Yeah. Yeah. Other questions? All right. Then let me show you the assembly instructions and the test program for this Whisker program. So here you can see kind of a closer view of the chassis, and hopefully you can see kind of what I was talking about there. So you can see that the whisker is attached to the chassis on the corner there. It's a little bit hard to see with the glare, but the whisker comes out and it goes past this 3-pin header here. That's what these 3 wires sticking up are. And when something bumps into the whisker, it moves back and it bumps and it touches that 3-pin header. And then when you're just driving along, the whisker is held away, and that it's not touching that header. Okay? All right. So if you want to work on this challenge, you can find all of the files under DT302, and then L04 whiskers and navigation, and then under whiskers. The whiskers project file has all of the instructions for how to assemble how to attach the whiskers and how to create this circuit. So, so you would start there. This shows the circuit that we talked about on board. And then this shows how to create that on your breadboard. So you should put that together if you're going to work on this. And then once you have assembled your whiskers, you want to test them out. So there's a test whiskers program. And what this does is this program runs. Okay, I gotta plug in the stand. This program runs, and it allows you to see whether you're actually getting inputs from the whiskers. So here, this debugging window shows the voltage on pin 5 and the voltage on pin 7. And those are the 2 pins that you use to detect the signals from the whiskers. So right now, it says pin 5 is 1, representing high voltage, and pin 7 is also 1, representing high voltage. Now, we can look at the Bobot, and if I push on one of these whiskers, I'm touching the whisker to the header now, and you can see that the voltage on pin 7 goes to 0. So when I push that whisker, the voltage on pin 7 goes down because that whisker is pulling the voltage down to 0. Let it go, it goes back up to 1. So that shows me that that whisker is working properly. And I can do the same thing for the other whisker. I touch it to the header, and the voltage on pin 5 now goes to 0. Move it away, and it goes to 1. So if you can do that for both of your whiskers, that shows that those inputs are working properly and everything is hooked up correctly. Okay? So that's your test program that you can use. And then once you have tested that out, you can run this program called Roaming with Whiskers. And this program does what we discussed earlier. It goes straight when there's no inputs, and then when it senses an input from the left whisker, it backs up, turns to the right, and goes in that direction. When it senses input from the right whisker, it backs up, turns left, goes in that direction. So again, you don't actually have to modify this program. This one is already written. I recommend that you take a minute and look through it and try to understand how it's working, but that's, you don't have to make any changes. So when you have assembled your robot, you can just run this program, and then you should be able to just let your robot go and have it cruise around, and then when it bumps into something on the right, it should turn to the left and go that way, and vice versa. Okay? So that is the main program for the robot. So, any questions about that? Yeah.
Yeah, would it be difficult to apply a program or this program specifically to something larger than grab this?
No.
Or like their bigger motors or bigger wheels?
No, you could definitely apply this program to something bigger. In fact, this company has made a promotional version of the Bobot, which is about 4 feet long and 3 feet wide. And yeah, you can run exactly the same program. Just hook up the bigger motors. Yeah. All right, so then let me take attendance. Yeah. Yeah, that's exactly right. So this is very much like a Roomba. So a Roomba goes around and it tries to avoid things. And yeah, it's exactly the same. Yeah, just like you said, using different sensors. I think the Roomba has laser distance sensors rather than physical Whisker sensors. But yeah, same exact idea. Yeah. Yeah.
Instead of the 220 resistor, could you have a diode there instead? So that if the P5 was for output, it just wouldn't go to the rest of the circuit?
Yeah, that's a good point. Yeah, you could put a diode there facing towards the pin, right? And then that would. So, well, but not quite, because basically it wouldn't allow the ground to pull the voltage down. Basically, what happens is that if you had a diode here, so like you mentioned, it would protect this pin because if you made this a high voltage, then this would block any of that voltage from flowing down to ground if the switch was closed. So that would be great. But even if this was an input, when the switch was closed, there would still be just a little bit of charge left on there that would be keeping this at high voltage. And this diode would prevent that charge from being pulled to ground when the switch closed. So it would just always see a high voltage. But yeah, I love that you're thinking about this and thinking about different ways to do it. And yeah, I encourage you, try things out. Try different ways of doing this and see what happens. And this is pretty much how circuits get designed in the real world. People say, okay, I'm going to build something, and they try it out, and then they go, oh, it didn't work, yeah. Huh, why did that happen? Oh, I see. The problem was here. Okay, well, we'll put in a part and fix that. So that'll be better. And then they try that out, and they go, it still didn't quite work. What can we do? Oh, we can add another part over there. And they kind of just keep, adding stuff in until it actually works. And then they said, yeah, well, that's the way I planned it all along. I just wanted to see if everybody was paying attention. Yeah, so that's how it goes.